Good morning, everyone. I'm Vamsi Ritvik from NIT AP, third year EC department. Today I'm going to explain about our course project, where I selected my project as robotic path planning using particle swarm optimization using MATLAB. So let's start with particle swarm optimization. What is it and everything I'll explain right now. So particle swarm optimization is developed by Kennedy and Ebenhardt in 1995. It was based on the behavioral swarm behavior of fish, birds and other ants, etc. This swarm behavior is studied for many years, and from this behavioral pattern of these small animals, they have developed this particle swarm optimization technique. So, what is particle swarm optimization? It is a population-based optimization algorithm which was developed by Kennedy and Ebenhardt, as I said before. So in PSO there is a population of candidate, also known as particles, which moves through the search space to find the optimal solution for the given problem. That is our main motto in the PSO. So for every PSO problem there are going to be two main parameters: position of the particle and velocity of the particle. These two are very important because they will give the experience of the particles and update it so that they reach the best possible position. To explain the particle swarm optimization more clearly, I am going to start with the one-dimensional space. So let's assume that there are two people who want to find the depth of the uneven lake. These two candidates are particles in this problem. Assume that these two particles start at the two endpoints of the lake. So one person is A and one other person is B. So let's assume it like this. When both person A and person B will measure the depth of the lake, I will show you. Both person A and person B will measure the depth of the lake. If the measured depth is lesser for A, then the person A will move forward, because we are going to find the global minimum. Depth should be maximum. After moving A forward, now after moving A forward, now the new position of A is this one, but the B position will be remaining the same. So now when they measure depth, the measured depth will be even higher compared to the initial position of the B. So now B will move forward and the location is updated. Now the measured depth of B will be higher compared to depth of A. So A will move forward. After moving A forward, again the depths are measured for both A and B, and A is again lower, so it will move forward and it will reach this step. This is now from visualization we can say that this is minimum, but the computer doesn't know that and we can't visualize all the steps, so we need to confirm that this is the minimum by going through next iteration steps. Now in the next iteration, since B has a smaller depth value, B will move forward and reach this position. This value is still lesser than compared to A, so it will again move forward, and this is still lesser compared to A, so it will again move forward till it reaches the same point as A. Then both A and B will reach both A and B, which are the particles which are going in a one-dimensional space, while measuring the depth of the lakes, which is the function value. which is also the like weight of the function. So by using this we found out that this point is the minimum point of the lake. This is the particles from optimization method in a one-dimensional plane. Now we'll look into the general particles from optimization. In particles from optimization, for the above example, to find the global minimum, we need two parameters as we explained above. Those are position and velocity at a given instance, given time instant t for particle I. These two are represented like this. Now, to find the best position to which a particle should move can be defined here. So, how to find the next position of the particle is using this formula, where we'll add the initial position to the velocity of the particle. So it will be like this. In there, these are the explanations about the particles and everything, velocity of the particles and position of the particles. And PI of t is the best location of the particle. So assume that we have a particle I, and then this particle will always store its best position, so that this best position can be taken as a reference or as a personal best for that particle. And g of t is the global best of all the particles. So these two are taken into consideration for updating the velocity of the particle for the next instance, so that it can be used to make the particle go into the direction of the absolute minima or global best position. So this is how the particle is moving in vector representation. This is the initial position, this is the velocity, and when you add these two you will get the yeah. And from this va of t and these two we will get the va of t plus 1, as va of t plus 1 is a equation that is compromising of both pa of t, xi of t and g of t. By using this one and this one we can find the next position of the particle. This is the general equation for the velocity of the time instant t plus 1, where w into v of t is initial component, c1 c2 are the acceleration components, this is the cognitive component, this is the social component. So cognitive component will be telling us about the personal best, or it tells more about the personal influence on the particle to reach the minimum position for a minimization problem. And the social component is global influence of on the particle for reaching the minimum position. C1 and C2 will be constants, but R1 and R2 are random values. As I said here, randomly distributed, uniformly distributed random variables. Next, so application. So as I said before, I'm going to use this particles from optimization to apply it in the robot path planning. So before that, I'll explain you what is robotics. Robotics is a branch in engineering that involves conception, design, manufacture and operation of robots. So it's a very complicated topic, and so I'm not going to go that deep into the robotics. So, for example, I'll tell you the objective of the robotics field currently. It is to create the intelligent machines that can assist humans in variety of ways. This is the current objective of the robotics, so that they can make the intelligent objects which helps the people make a better life. So, and robots can be of any form. It may resemble a human, or it can take uh, car form, or drones. Drones as a form of a robot known as UAV, unmanned aerial vehicles and everything. And in working of the robots, we are going to talk about another big application in it, which is also called as robot process automation, where we try to automate all the process of a robot, because a robot is all about making an intelligent life form, and the intelligence also has to have an automation. So we are going to work on the automation process in this topic. As robotic automation is a rising domain of study within the last 2 decades, and it is also a very important for robots to know what it's doing, learn from its mistakes, and help the humans better. So a robot needs to be aware and plan the best possible options of its by itself to be called as a proper automation. The awareness part can be done by using the sensors, but the planning should be done by using algorithms. The algorithms which I am currently using in this topic is particle swarm optimization. Where I am going to use it is in path planning and control assistance of the robot. So we will use the particle swarm optimization to find the best path to take to reach a destination while avoiding the objects or obstacles in between by in the smallest path possible. So utilization of particle swarm optimization to find the optimal path to the robot for the robot. Yeah. So as I said before, it's a technique that uses many particles initially and updates the velocity function to make the particle go in the best path in with every iteration. So this is a little different from the general explanation I have given, because in general explanation I have told you that all the particles will start at the same time, and the velocities will update it with every instance. But in my scenario, although we use it in a similar way, but we are going to update it with the every iteration. So you will get the best output in like output with every iteration. So what we are going to do? Initially we are going to create a map for the particle to move from a point A to point B. That is, it needs to have a started in positions, and we have to create few obstacles in between to make the robot go around the obstacles. And we will write a cost function. So what is a cost function, you may ask? Since our goal is to minimize the path of the, like, take the shortest path, the cost function will be the length of the path it took to reach the endpoints from the start. That is the objective function of our optimizing problem. Now we will use the PSO algorithm to minimize the length of the path taken by the particle. And out of all the particles we get, we will choose the best particle and we will take the path it took, and we can implement it to the, like we will implement it in our robot, physical robot. So the simulation, before I show you the simulation result, I'll show you the simulation once. So this is the MATLAB code for the particles quantumization and robot path planning. So first I'll show you this. As I explained before, this is the function for creating a model, and this is the position of source and destination, and this is the coordinates and radius of the like obstacles in between. You can increase this by changing the number, like add one more for the x and y and r, and here n is 4. This will create a map or a model from where the particle can move, and this is the like initialization or creating a random solution. We use this function to create that. Now, so this is the cost function where we will find out the length of the path taken, and here you may observe we will also use the parse solution. Parse solution is a like this is a code for making the points within the like we will get a few points through which the point will curve, like the function will curve. So we'll use this parse solution function to make it as a soft point so that the code will understand what we do, like how to optimize it better. And this is the code for plotting the equation, plotting it, and this is the main code. As you can see, we have created a model and initialized all the values, and also given the upper and lower bounds for the variables. This is the cost function. We defined it using this function, my cost function. Given the parameter values as number of iterations, population size, inertia weight, damping size, damping width or ratio, and these coefficients, we gave everything. Then this is the initialization part where we initialize it everything, all the values. After initializing it, we are going to start the main loop where we update the value of the velocity and everything with every iteration so that the best positions and everything are updated by using the general velocity function. Update the bounds, position, velocity mirroring and everything. And this is for the y part. Since it's a coordinate system of 2 dimensions, we are going to do it x part and y coordinate separately, then update it. We are doing this bounding and mirroring is because we also have the obstacles in between. We make it so that the particles always avoids the obstacles, and update the best positions along with the cost. Then we will show the iteration information in the command window, and we'll plot the graph. So I'll show you this. As I explained everything, I'll show you the code once. I'll run it once. See, with every iteration it's updating. By updating its position, velocity, and everything, it's going to update it. And since we used a parse solution, we created these points where the line is going to curve. This curve will help the robot to plan the path more accurately. And this is the cost function, and this is the final best and updated position. We can use this coordinates and directly dump the like coordinate values with a proper code so that it can directly be used for the robot. And this is how the code optimized everything. As you can see, everything is almost optimized around 25th iteration. So there is not even need for going to the 100th iteration. So my code solution could be got to the 25th iteration. And this is how my code works. Thank you. Since I explained my code, I'll come back once again to the PPT where I'll show you my simulation result initially. This is the simulation result. As you can see here also, I got the solution at the 20th only. So we don't need to go till 100th iteration. And this is the minimum path. Almost same as the what we previously saw. And these are the differences. You can also find the papers and tutorials and everything from my references. Thank you.